Hello guys, we're going to have a look at applications of integration in this session, and it is a very important session because in this session we're going to be dealing with the average value of a function, which just comes up all the time. Okay, let's go. The average value of a function, ladies and gentlemen, the average value is actually about integration. Now, I want to say right at the outset that it is not to be confused with the average rate of change, which is simply y2 minus y1 over x2 minus x1 for some function y is a function of x. It's not to be confused with that, and it does get confused with that all the time. So take as an example y equals 2x, and we want to find the average value of y over the interval x going from 0 to 3 inclusive. The first thing we do is we find the actual integral of that function from 0 to 3, and if we do that we get 9 square units. You notice I'm saying integral, not area. It's actually an integral, a signed area. In this case it doesn't matter because the function is above the x-axis for the whole of the integral over which we are integrating it. But I just need to put that caveat in because it's going to come up later in another example I will show you. So there's the function, yes? And we get 9 square units of area, well, signed area, but it's just the same as area in this case, for the integral from that interval 0 to 3, okay? Now, the average value of y over that same integral is the constant single value of y, which gives the same result of the signed area over that same interval. So if we were to draw a value of y on that y-axis and do a horizontal line from that point on the y-axis right across to where x equals 3 and work out the area of the rectangle underneath that line y equals y average, then we would get the same signed area as we got from the actual integral. Now, I will show you. So we're saying that y average times 3 is the same signed area as the actual integral over the interval concerned. Okay, so y average is actually 1/3. We're dividing by the width. We're just solving for y average, right? That's the width. So we're 1 over the width times the integral of 2x with respect to x from 0 to 3. Now let's show you that on the diagram, okay? So this area here, this rectangular area, which I've hashed in red stripes here, horizontal stripes, is the same signed area as we're getting here from the actual integral. Okay, that's how it works. That's how it works, guys. It's a very simple concept, so you'll get it and you'll be fine with it. Just don't go confusing it with the average rate of change like a lot of students do. Okay, in general, so y average times the width of the interval from a to b, which would be b minus a, is equal to the actual integral of the function from a to b, okay? And y average equals 1 over the width times the integral from a to b, okay? Here's an example for us to get this straight in our heads with. Example 1, find the average value of the function y equals x squared for the interval x going from 0 to 3 inclusive, okay? So there it is. There's the graph of y equals x squared, and we've hashed in green what you would get for the signed area from 0 to 3 in the x department, all right? So we've got that integral there, and that's equal to that, yes? And when we work that out, it comes to 27 over 3, which is 9, okay? So that is the signed area under that graph from 0 to 3. Now for the rectangular equivalent area using y average, we know that y average times that same width, in other words a rectangular area, would also equal 9 units, okay? So therefore y average would be 9 over 3, which would be 3 square units of area, okay? So there it is over there, do you see? I've drawn it in, so that's y equals 3. If you draw that horizontal line over there, in other words the same y average value over the whole interval, getting to x equals 3, and you basically work out the area of that red hashed rectangle, it's the same as the signed area of this green hashed area here. Okay, pretty simple, huh? Alright, let's do another example now. We'll do a tricky one. Find the average value of the function y, or f of x, equals sine x, where firstly x goes from 0 to pi, and secondly it goes from 0 to 2 pi, and something amazing is going to happen in part B. Okay, first of all, part A. There it is, okay? So we're saying there's the integral of sine x with respect to x from 0 to pi, and that would be minus cos x, and we're going from 0 to pi, and we will get that minus cos pi, which will be minus 1, plus cos of 0, which is already 1, so it looks like we're going to get 2. Yes, amazing. Therefore, y average will be 1 over the width, and the width is pi, times the integral. Are you getting the hang of it now? Hopefully you are. It's pretty simple. And the answer is 2 over pi. Yes? Great. And there it is. See, I've hashed it in to show you. See? That average value there, which I'm pointing at with the black arrow, is 2 over pi, and that red hashed rectangle has the same signed area, in this case just the area because it's all above the x-axis, as this graph here. Okay? Great. Let's do part B now. Now this is where the amazing result happens. Okay, we've got this now. We're going from 0 to 2 pi, so the graph is wobbling, oscillating above and below the x-axis over one complete cycle. And the value of y average is equal to 1 over the width, which is 2 pi, times the integral of sine x with respect to x from 0 to 2 pi. Now, ladies and gentlemen, if you care to work that out on your calculator, or if you care to get a piece of paper and work it out manually, the integral of sine x with respect to x from 0 to 2 pi is exactly what? What did I hear you say? Yes, it's 0. It is 0 because you have this self-compensation thing, this cancelling of a positive signed area with a negative signed area here. So that gives you the amazing result that the average value is in fact 0. And when you think about it, it does really make sense because the average value for this sine function over one cycle is simply the value of y about which it oscillates, which is 0, isn't it? Yes, so we are talking about a signed area, not just an area, okay? Integrals, not just areas. And if the graph dips below and above the x-axis, then you have to take that into account. Yes, you do. Yes, that's plus and that's minus, okay? Good for you, you're getting it. Now, we're going to finish off this lesson with some kinematics, motion in one dimension, which is also on the methods course, okay? So, even though it doesn't come up very often, we might as well deal with it because it is on the syllabus. Alright, example 3. A body starts at the origin and it moves in a straight line with velocity given by v of t equals 2t minus 3, where t is greater than or equal to 0 because it's time, and the distances are in metres. Find the following. Firstly, its position at any time t. Secondly, the position after 1.5 seconds and after 5 seconds. In part C, the average velocity over the first 5 seconds. Part D, the distance travelled over the first 5 seconds. They're always booby trap questions, by the way, because you will find when they ask you that it has changed direction, and therefore the distance is not the same as the displacement, so watch for that. And part E, ditto, we have the same problem. The average speed over the first 5 seconds is just the distance over the time. So if you get the distance wrong, the average speed will be wrong. Okay, let's do it now. Part A, the position at any time t. Well, in order to do that, we have to anti-differentiate the velocity, okay? So we just do that, and we get t squared minus 3t plus c, and we have to sub in our boundary conditions, where we know that x is 0 when t is 0. It starts at the origin. That's what that's saying. When we sub that in, we get c is 0 anyway, so that was a bit of an anticlimax. And we get x is t squared minus 3t. Okay, we're off and running, guys. Now, let's do part B now. Part B, the position after 1.5 seconds and at 5 seconds, we just sub in the times, yes? Okay, so subbing in t is 3 over 2. We would get x is 3 over 2 squared minus 3 times 3 over 2, which comes to 9 over 4 minus 9 over 2, which gets us minus 9 over 4. That's its position Therefore, its position, if you like, you can just leave it like that, or you can say it would be 9/4 metres to the left of the origin, if you want to get all fancy. But look, time is of the essence in an exam setting, so that's good enough. Yeah, the minus tells you it's to the left, and the 9/4 tells you how much distance. Now we sub in t equals 5, and we do the same process with t is 5, and we'll get x is 25 minus 15, or 10. 10 metres to the right of the origin, if you want to put it that way, yeah? But that answer is quite adequate. Now part C, for you and me, the average velocity. Now this is where you have to be taking the average rate of change of position, okay? Now, in this situation, we're only concerned with the final position and the initial position, okay? Because it's average velocity, so it goes like that. X at 5 minus x at 0, that's the change in position over the change in time. That's the average rate of change of displacement, which is the average velocity. So we've got 10 minus 0 over 5. We worked out the 10 here, didn't we? Yeah? And we're told that it starts at the origin anyway, so when t is 0, x is 0. So it looks like it's going to be 2. Okay? It would be 2 metres per second average velocity. All right, guys, we're running hot here. Let's do part D. Now, this is where you've got to be very, very careful, okay? So I always like to draw a little graph just to get myself sorted on what's going on. So we can see here's V equals 2t minus 3 given over here. And we can see if we draw that graph from t is 0 onwards, we can see that from here to here, the velocity is negative, and it hits 0 at 3/2 seconds. And then from here onwards, up towards our 5 seconds, or beyond even, we've got a positive velocity. So in other words, this thing changed direction when t was 3/2. So that has dramatic implications when we're trying to work out distance, okay? So what we'll have to do is we'll have to work out the change in position from here compared to here for the first part of the journey, which was going backwards or in the negative direction, strip off the minus, which we'll get in terms of the displacement from here to here, and then in the second part of the calculation we'll have to work out the change in position from this time to when t is 5, and then we'll have to strip off any plus or minus from that component of the journey, just leaving distance, and then add the distance for this part, the negative direction part, and then add that to the positive direction part, and then we have the distance travelled over the first 5 seconds, okay? It is different from displacement because the particle changed direction when t was 3/2. You might like just to get yourself standing where there's plenty of room and simulate the journey yourself by moving backwards for 1.5 seconds and then start moving forwards and speeding up, okay, when you move forward. So moving backwards, slowing down to 0, and then moving forwards and speeding up. That's what's going on, okay? All right, it's very important. That's why I want to emphasize that. So yes, we know V is negative for the first part of the journey from t is 0 to 3/2, and V is positive for t is 3/2 to 5 seconds. So we change direction, okay? So I'm working out the first component of the journey now, where we're going from t is 0 to 3/2 seconds, and I'm getting that for the displacement. There it is. So therefore the distance is just 9/4, okay? The second part of the journey, from 3/2 seconds to 5 seconds, we've got a displacement of that, which gets us 12.25 metres, okay? Now, what we're going to do now is basically just add those two distances up, the two distances, okay, with the pluses or the minuses stripped off. So therefore we get 58/4 if we add it up, because 4 12s are 48 and 1 is 49. 49 and 9 is 58. 58/4, which is 29/2. and that is our distance in metres, okay? Part E, the average speed over the first 5 seconds. Well, that's easy now because it's just the distance over the time. Okay, so it's going to be 29 over 2 metres divided by 5 seconds, which will get 29 over 10 metres per second, average speed. All right, that's it. We're finished. So thanks for being with me, and I hope you got something out of that. Go forth and multiply your knowledge, and we'll see you soon.